Hi everyone, in this lecture we are going to talk about recursion basics. So many people get fear when they hear the word recursion because it's a pretty confusing technique, especially for the beginners. But we will try to explain you it in a simplified manner with the help of certain examples, and we will do a lot of problem solving on recursion as well. So let's see what is recursion. So as I said, it's a technique in computer science where a solution to a problem, depends upon solution to smaller instances of the same problem. This is something that what you need to remember. So let's say you have a problem, and that problem is a complex problem. That means it has a larger input, let's say, and you want to break this problem into maybe smaller instances of the same problem. Maybe you break this into, let's say, three sub problems of, let's say, size n by 3, n by 3, n by 3. So our idea would be to solve the sub problems and combine the answers of sub problems to get the answer for a bigger problem. So that this is something what we would be doing. And what is the meaning of smaller instances of the same problem? Let's say we want to compute some function f, then the smaller problem will also be on the same function f. Something like this. So I will try to explain you with the help of one very simple example. Let us see the most classical example that is taken to uh, teach recursion. So that is the factorial question. So let's say I want to compute a factorial of a number n. Let's say that number n is 5, and I want to compute f of n that is equal to n factorial. This is something what I want to compute. Now, although this is a easier problem, but we can break this problem recursively. We can break it into a smaller subproblem of the same type. So you know what is the property of factorial. So n factorial is nothing but it can be written as n into n minus 1 factorial. And what is n minus 1 factorial? It is nothing but f of n minus 1. So it can be written as like this. So what we have done, we have written a larger problem in terms of a smaller subproblem of the same type. Now, how do we compute it algorithmically? For example, if I want to compute 5 factorial, so this will be written as 5 into 4 factorial. This 4 factorial can be written as 4 into 3 factorial. This can be written as 3 into 2 factorial. This can be written as 2 into 1 factorial. This can be written as 1 into 0 factorial. At 0 factorial, we know we have reached a point where the problem cannot be broken down further. So such a point is known as base case. So let us see what are these terms. So at this point, we would say we have reached a case which is known as base case. That means we cannot reduce our problem further, and the base case is the case where we know the answer of the subproblem. So 0 factorial is nothing but 1. So what we will return? We will return 1 into 1, 1, and this 1 will go back here. So this would become 2 into 1, that is 2, and this 2 will go back here. So this is nothing but 3 into 2, that is equal to 6, and this 6 will go here. So 3 factorial will get replaced by 6. This would become 4 into 6, that is 24. This 24 will go here, and 5 into 24 would be 120. So when we would be dealing with recursion, we will see two directions. In one direction, we are breaking the problem and we are trying to simplifying it. So that means we are moving towards the base case, towards the base case. And another direction would be in which we are again coming back from the base case towards the main problem. So this is from top to down, and this is from down to top. So we would be doing work in two directions. First, we would be breaking and simplifying the problem, then we would be combining the solutions to form the answers of the bigger subproblems that we have left. So this is how this recursion is going to work. Now you may ask, how does it will work in the form of a program? So when we are going to write the code, we will take the help of call stack, function call stack. So I hope you remember the call stack concept. So what happens is, let's say you have a function main and it makes a call to the function hello, which further makes a function call to the, let's say, to a function hi. So what happens is, in the call stack, you will see that these functions will get stacked on the top of each other. And in the order in which they are called, and once the function hi is completed it will go off, once the function hello is completed it will go off, and once the main is completed it will also go off. So recursion actually uses the concept of call stack to store all the states of these variables that we are going to have. Okay, so it will become more clear as we go through some more examples, but for this video the concept is you understand at high level what recursion is going to do. It is going to break down your complex problems into smaller sub problems. We are going to solve those sub problems and get back our answers. Okay, so let us see another example. So for example, we want to define an operation, go to home. Let's say you are standing at some coordinate, let's say some x coordinate, and your home is at some value that is equal to, let's say, n. So you want to reach this home, and what you will do, so one is you put a loop, and you can simply do take one step every time. But another thing you can do is you will say, okay, no, I will just take one step and I will ask recursion to take me home from x plus 1 till the n. Okay, so the idea is you take one step and leave the rest of the work for the recursion. Okay, so this part can be solved recursively. Again, in this part what you would be doing, take one step, leave the rest, work for recursion, take one step, leave the rest, work for the recursion. Okay, and what would be the base case? The base case would be, if you are at the home, stop moving, you don't need to go anywhere. In the recursive case, okay, the other case in which we defined a recurrence like f of n is nothing but n into f of n minus 1, this case is known as a recursive case. So what would be a recursive case for this problem? You will take one step towards home and you will call the same function go to home from x plus 1. Okay, so if I show you in the form of a little bit of a pseudocode, so this is how the code would look like. So there is a method go home which gets the current location, and it also gets where the home is located. So you check if we have already reached the home, we will say okay, we have reached the home, and return. We don't do anything further. Otherwise what we do, we take one step and we call go home from that particular step. Okay, so this is how a recursive code would look like. So you can see we are calling the same function because we said that we are going to break down the problem in terms of a smaller sub problem. Okay, so here also we have broken down, if we need n steps to reach the home, so we have taken one step and we said okay, the remaining n minus 1 steps will be taken by the same recursive function. So this is a pseudocode, and the idea is you understand at high level what is recursion is going to do. So recursion also related with the idea of principle of mathematical induction. So you might have studied about this principle while in your school or in college. So in this principle, what we actually try to do is we first figure out the smallest case. Maybe we see what could be the smallest possible solution for the given problem. Maybe what could be the value of f of 0, maybe what could be the value of f of 1. So this will depend upon what kind of question it is. Okay, so in some cases we may have f of 0, f of 1, maybe f of 2 as well. So we want to figure out what is the value of the smallest case. For example, in case of factorial, the smallest case is 0 factorial, that is 1. Okay, in case of a Fibonacci, there would be two smallest cases, because to build Fibonacci series we need two initial values, 0 and 1. Only then we can build the next value. So this we will look at later on as well. First step is always figure out the smallest case. Then when you're writing code for the recursion, one assumption that you always need to take is, suppose you're breaking down your problem f of n in maybe two sub problems, f of, let's say, n by 3 and maybe f of 2 n by 3. So what you need to assume that sub problem can be solved. Okay, so you have to assume that these two sub problems will be solved recursively. Using this assumption, you have to write a recurrence. Okay, you have to write a recurrence for f of n. Okay, how I can combine the solutions of the smaller sub problems to get the answer for f of n. So once you do this, your code will work fine, and you can also verify and think why your code works. Okay, so you have to solve the current problem assuming the sub problem solution exists. Okay, so this is our assumption, but it will actually work, and we will prove it why it works. So we have to find out, okay, let us assume that sum f of n minus 1 is true, or using this we will find out, okay, what is f of n in terms of f of n minus 1. Okay, or n minus k or something. Okay, so it could be any sub problem, it can be broken down in any way, and it will depend upon problem to problem how we break down the problem into sub problems. So this is a high level introduction about recursion, and in the next lecture we will actually see an example along with the code. That's all for this lecture. Thank you. Hi and welcome back, and now we are going to deal with the first example of recursion, that is how to compute the factorial of a number. So we have already seen that f of n for factorial can be written as n multiplied by f of n minus 1, and for example, if we have 5 factorial, it can be written as 5 into 4 factorial. And we discussed when we are going to solve a recursive problem, we will figure out two cases. One is a base case and second is a recursive case. Okay, so in the base case, I know when the value of n is equal to 0, the answer of factorial should be 1. And in the recursive case, I know the formula is nothing but n multiplied by f of n minus 1. So these are the only two things that we need to know. So once we know these two things, we can write the code, and while after writing the code, I will tell you how the call stack works and why we are getting the right answer. Okay, so we will also talk about call stack in recursion and why it is correct. So let us first dive into the code and then we will see. So I'm going to make a recursive program for factorial. So let us say we have a function int factorial. The return type is integer because the function is going to return an integer. So we get some value input, and we have a base case, and we also have a recursive case. So what is going to happen in the base case? We are going to say if n is 0, then we know the answer is going to be 1. That's it. In the recursive case, we know that the given problem f of n can be written as n multiplied by fact of n minus 1. That's it, and we can say return this answer, and we are done. Okay, so this is the complete factorial program, and now we are going to test our code. So maybe take input from the user and print the factorial of that particular number n. So build is successful, so let's run it. So if I give 5, I get the answer as 120. If I give 6, the answer is 720. That means it's working perfectly fine. And now let us also look what happened actually. So when your program started, okay, so there is a call stack, there is a concept of a call stack. So what is call stack? Stack is a special memory, so it's like a container, and all the functions that are called, they go inside the stack. So first of all, the main function, it went into the stack, and all the local variables like n, here we have only one local variable, so that is defined here. And let's say we took this value as input, so n is defined as 5. So from here we call the fact function and we tell, okay, we have to compute the factorial of n equal to 5. So this checks whether the base case is true. So this is not true. It makes another recursive call. Okay, you can see it computes a value answer. So there is a variable answer that is not yet computed. So it is 5 into something. So that something is what? That is factorial of 4. So we make another recursive call to the factorial. That call gets pushed into the stack where n is 4. And here we also create another local variable because answer is a local variable. Okay, so in every call stack we are going to create these local variables. So here the value of answer is 4 into something. That something is another function call, will return. Okay, so n equal to 3. Here we have answer equal to 3 into something. That something is nothing but another function call. N equal to 2. Answer equals to 2 into something. That is f of 1. So we make another function call, and that answer is 1 into 0 factorial. So we make another function call with n equal to 0. So now when n is 0, we say return 1. So this function actually returns 1. It gets removed from the call stack. So here I will change my color. Now we are going to work in the different direction. Now we have reached the base case. Okay, and the base case says you return 1 to the point from where it was called. So it was called from here, so we return a 1 here. So it becomes answer is 1 into 1. Now f of 1 is going to return 1 and you can see return answer. Now this statement, earlier what happened is when you were computing this answer, this function was paused at line number 12 and it was waiting for the value of fact of n minus 1. Okay. Once it got a value from fact of n minus 1, it returned the answer, that is 1 into 1, that is 1. So this gets removed from the call stack and this answer 1 is stored here. So it is 2 into 1. Now this function was waiting for the value of f of 1 and now it has got the value because this function returned to its parent. This will get removed, so it will return 2 into 1, that is 2. So 2 will come here. Similarly, this function was waiting for f of 2. Now that value has arrived and it will return 6. So 6 will come here. So it would become 4 into 6, that is 24, and it would return 24 here. It would become 5 into 24, that is 120, and this value would come here because main is waiting for this value. So here you will get an answer of 120. That's it. And finally, once your main is also over, this also gets removed from the call stack. Okay, so if I talk about how much time it will take, so we actually made a call stack of n levels deep. So we are making n number of calls. Each call takes constant time, so the time taken is order of n. Okay, so time is order of n. And what about the space complexity? Okay, so if I talk about how is the space complexity changing throughout the entire program, so initially you can see there was only one stack frame, that it increased to 2, 3, 4, 5, 6. Then it came back to again like 0. So during the point when the base case was hit, the space utilization was maximum and that was equal to order of n. Okay, so in the worst case, or during this entire execution, so this is space and this is time of execution. Okay, so at a particular point the space utilization was maximum, so we would say the space complexity of this program is also order of n. Okay, although we are not taking any extra array, but we are using the call stack which takes memory, and you can see for maximum depth of n we have created n number of answer variables, each storing a different value. Okay, so at a particular point in the program the space utilization went up to linear, so we can say both space and time are going to be order of n for this problem. And one point you need to remember, that all recursive problems will take up extra space. Okay, so recursion actually takes extra space because of the concept of this implicit stack. Okay, so that's it, that's all for this lecture, and now I hope you understood how recursion actually works for this particular problem. Hi everyone, in this lecture we are going to learn how to write a recursive function to compute nth Fibonacci number. Okay, so if you have not heard about Fibonacci series, I will tell you it is a very simple mathematical series in which the first two terms are 0 and 1, and every term, every ith term is the sum of previous two terms. Okay, so I can say the nth term is nothing but it is sum of previous two terms. Okay, f of n minus 1 plus f of n minus 2. And if I talk about what would be the next term, it would be sum of these two, that is 1. What would be the next term? Sum of these two, that is 2. The next term would be 3. The next would be 5. The next would be 8. The next would be 13, and so on. Okay, so what we are given a particular value of n, and we want to tell, okay, what is the nth term of this particular series. Okay, so for example 0, 1, 2, 3, 4, 5, 6, 7. The 7th term of this series is going to be 13. The 11th term is going to be some xyz. The 5th term is nothing but 5. So we need to figure it out. Okay, so as I said, when we are dealing with recursion, we will need two things. One is a recursive case that we've already seen, we already know about this problem, and second is the base case. Okay, so the idea of picking this problem is not to teach you the code, because code is very simple. The idea is to teach you the concept of recursion when there is more than one call. In the previous question we saw there is only one call happening from each function call, but in this case from each function call two calls are going to happen. Okay, so we will talk about how the recursion tree would look like in this case, and what would happen to the call stack and so on. Let's also talk a little bit about the base case. So base case is going to be two cases. Let's say you're computing for n equal to 2. So 2 is going to make two calls, one on 1 and one on 0. But now at 1, what you are going to do? Will you make two more calls? Will you make a call on 0 and -1? The answer is no. We cannot make calls on the negative indices. So that means we have to take 1 as a base case and we have to take 0 as a base case. So this part is not needed. So we will have two base cases here. The value of n equal to 0 is going to be 0 and the value of n equal to 1 is going to be 1. So let me first show you the code, and then along with the code we will try to dry run how this code is going to work. Okay, so let's make a new program for Fibonacci, and let's copy little bit from here. So this is now fib and this is now fib. So as I said, we are going to have two base cases. Okay, so I can put both of them in a single condition. If n is 0 or n is 1, we can return n. That means if n is 0, we are returning 0. If n is 1, we are returning 1 actually. Otherwise, we are going to say we are going to compute two values. One is f1, that is fib of n minus 1. Another value is f2, that is fib of n minus 2. And our answer would be nothing but f1 plus f2. Okay. So we could have directly written return fib of n minus 1 plus fib of n minus 2. But just to make things easier for you, for the first time, I have written the code like this. Okay. Now this will also make the understanding of call stack more clear. What is exactly happening? Now this is the code. Let us first run it, and dot slash Fibonacci. If I say okay, tell me the 7th term, it is 13. Tell me the 5th term, it is 5. That means it is working perfectly fine. Now let us see what happens at the call stack level. So let's say this is our call stack, and I'm going to run it for a small example. Let's say for f n equal to 4. Okay, and now in the beginning we had only main. So what happened is from main we made a call to f of Fibonacci of n equal to 4. So we called Fibonacci with the value of n equal to 4, and it tried to compute the value of f1. So it made a call to 3. So it called fib of n equal to 3. Okay, and at 3 what it did, base case is not true. It tried to make a call. So another call it will make, but it will make later on, that is to n equal to 2. These calls are not executed yet. These will be executed later. So 3 made a call to 2. So 3 made a call to 2. Okay, and what happened at 2? 2 must have made a call to 1. Okay, so fib of 2, it made a call to f of n equal to 1. Now at n equal to 1, we saw that this function hits the base case and it will not execute this code. It will return a value of n, that is 1. So 1 actually returned 1. So this actually got removed from the memory. Okay, so this actually got removed from the memory, and now what happened is so this branch is also gone. Okay, so this branch returned 1 and it is now gone from the call stack. Okay, so what is going to happen is 2 computed the value of f1. 2 is now going to compute the value of f2. This function will now execute line number 10 for the first time at this particular point. So it will make a call on 0, and 0 will return a value of 0. So it will make a call on fib with n equal to 0, and this is going to return 0, and this is again going to get popped off. This is going to get removed from the call stack. So at this point, this is how the call stack is going to look like, and 2 knows my answer is 1 plus 0, that is 1. 2 is going to tell 3 that my answer is 1. So 3 now only knows one of the answers. Okay, so 3 knows the answer of f1 for 3 is 1, and 3 is now going to compute f2, for which it is going to make another call. So this is going to get removed. This is going to get removed, And what is it going to do? 3 is going to make a call on fib of 1. Okay, so it is going to make fib of 1. So fib of 1 will get added in the call stack, and it will again return 1 to 3. So it will return, my answer is also 1. Okay, so at 3, what it is going to do? Now 3 knows that I know one answer was 1, the another answer was also 1, so it is going to return 1 plus 1, that is 2. And now 4 knows that my f1 is 2. So 4 gets to know that one of the answer is 2. Okay, and now 4 is going to make a call for f2, that is this line number 10, and this call will get executed. Okay, so we make a call at 2, so same story is going to repeat. 2 is going to make a call on 1, 1 is going to tell my answer is 1, it will get added to the call stack, then once it returns it will get removed, then 2 will make a call to 0, 0 will return again 0, and 1 plus 0 is going to be 1. And at 4, we earlier knew that one answer was 2, and f2 is now 1, so it is going to return 2 plus 1, that is 3 to the main. So fib of 4 is going to be 3. So I've not drawn the call stack completely, but what I am trying to tell you is, if you want to make it easy, if you want to see how many calls are made or what calls are made, so the ideal way is to draw it using a recursion tree. Okay, and from this you can easily estimate the space time complexity of the program as well. So what happens at n equal to 4, or let us do it for n equal to 5. So 5 will make 2 calls, 4 and 3. This call will happen later on. 4 will make 2 calls, 3 and 2. This call will happen later on. It will make 2 calls, 2 and 1. This call will happen later on. It will make 2 calls, 1 and 0. So 1 will execute first. So 1 will return 1, 0 will return 0, 2 will return 1, and 1 will return 1, 3 will return 2, 1 plus 1, and 2. Now 2 is not going to return anything directly because it is not the base case, so we need to further expand it. So 2 will make 2 calls, it is going to return 1, it is going to return 0, it is going to return 2 plus 1 plus 0, that is 1, and 4 is going to return 2 plus 1, that is 3. And now 5 is going to make a call on 3. 3 is not a base case, it's going to call on 2 and 1, it's going to call on 1 and 0, it will return 1, it will return 0, it will return 1, it will return 1, it will return 2, and 5 is going to return 3 plus 2, that is 5. Okay, now these are the number of calls that we have made, and roughly the number of calls in this case, if I talk about on the first level I have 1 call, on the second level I have 2 calls, on the next level I have 4 calls. So it is a GP, and we have roughly n levels, so approximately we are making exponential number of calls. The time taken would be the number of calls plus time in each call. So in each call we are doing a constant work, that is adding 2 numbers, so it is order of 2 raised to the power n. Now what about the space? How much memory we have taken? So in the worst case, the maximum depth of the call stack would be this much. Okay, because at any point only one of the branch is going to exist in the call stack. Okay, so the memory of the program would look something like this. It is increasing, then maybe decreasing, then increasing, decreasing, increasing, decreasing, and finally 0. Okay. So in this particular branch the utilization is maximum. Okay, so it would be something like of this kind. This is when n equal to 1 was hit, this point, and this was n equal to 0 was hit, something like this. At these 2 points the space utilization is maximum, so the time is order of 2 raised to the power n, the space utilization is order of n. This is how the Fibonacci is going to work. I hope the concepts are clear. That's all for this lecture. Thank you. Hi everyone. So now we have already looked at 2 examples in which we used recursion to bring a solution. Now we are going to look at a third question in which we are not given a number, but we have to work on an array. Okay, for example, we need to write a recursive function that checks whether a given array is sorted or not. Okay, so you may think, how do I apply recursion on an array? So the idea is very simple. Like we said, for a problem of size n, we can break it into one unit work we will do, and remaining n minus 1 units of work recursion will do. Similar thing we can apply here as well. So let's see how we can actually handle this problem. So let me draw an array, and let's say we have certain elements. Let's say 1, 2, 3, 5, 4, and 6. Let's say this is the array and I want to check if it is sorted or not. Now what you can do is, the first step you can take and you can ask recursion to tell whether the remaining array is sorted or not. Okay, so the first step would be you compare the 0th element with the first element. That is, you check if 1 is less than 2 and the remaining array is sorted, then you can say the entire array is going to be sorted. Okay, so what is the condition for array of size n? Let's say you have an array of size n. You can check it is sorted if array of 0 is less than array of 1. Okay, and let's say there is a function f that returns whether this array is sorted or not. So what we will need to do, we need to check if this is the case and the remaining array is also sorted. Okay, the remaining array is of the size n minus 1. If it is also sorted, then we can say yes, the entire array is going to be sorted. Okay, so what I'm going to tell, if 1 is less than 2 and 2, 3, 5, 4, 6, this is the remaining array, is this array sorted? Again, I will make a recursive call. Okay, so I'm breaking down this code. 2 is less than 3, yes. Then we will make a call on the remaining array, that is 3, 5, 4, 6. Then we break it down. Now for this array, a0 is less than a1, yes. 3 is less than 5, and we can check that the remaining array, that is 5, 4, 6, is it sorted or not. So now at this point we are going to check, is 5 less than 4? The answer is no. Okay, as soon as we get this answer as no, we don't need to make any further calls and we can return false from this particular point. So this basically tells, okay, this condition is false. It tells its parent that this condition is false. So here we are doing a AND of true and false. That means the output would be false. Here we are doing a AND of true and false. The output would be false, and hence to the main call we will tell, okay, no, this array is not sorted, and we are going to return. So this is the case for when the array is not sorted. Now let us also look at a case when the array is sorted. What is going to happen? Let's say, let me take a small example now. 1, 2, 3, and let's say 5. So we are going to check 1 is less than 2. Yes. Remaining array is sorted. We don't know. Recursion will check. It will check 2 is less than 3. Is the remaining array sorted? We don't know. Recursion is going to check. 3 is less than 5. And is the remaining array sorted? Remaining array has only one element. Yes, so one element array is sorted. This is true, this is true, it returns true. This is true, this is true, it returns true. This is true, this is true, it returns true. Hence this array is going to be sorted. Now from here you can figure out the base case. So if only one element is left, then you can say yes, it is a sorted array. Okay, in the recursive case you have to check for two conditions. One is if a0 is less than a1 and the remaining array is sorted. Okay, so remaining array you can make a recursive call to check whether that array is sorted or not. So that's all for this concept, and now we will look into the code. Hi, so now let's see the code for this problem, whether the array is sorted or not. So there are multiple ways to write the code. I'm going to discuss few of the ways. Okay, so in the first function I'm going to write a boolean function that tells whether an array is sorted or not. I take input the array, and I also take input the number of elements the array is currently containing. Okay, so we talked about we will have a base case, and we also talked about we will have a recursive case. So what happens in the base case, we said if only one element is left, or maybe 0 elements are there in the array, then it would be a sorted array, so I can return true. That's what we have already discussed. In the recursive case we talked about, we will check if array of 0 is less than array of 1 and the remaining array is sorted the remaining array. Okay, so now let's say this is the array, and the remaining array I want to start from this particular point. So I can pass this point as ARR plus 1 because it will take my array starting address for the remaining problem to the next index. So I can check if the array that starts from array plus 1 is sorted, and this array contains how many elements? This contains n minus 1 elements. Okay, if this is the case, then I can say return true. If one of these conditions is false, then I can say return false. That's it. That's the entire code. Now we can try to run and check. For this example, maybe I can just see out is sorted, and I give the array and I give the value n. Let's build the code and let's try to run it. So dot slash sorted array, and I'm getting a 0. That means this array is not sorted. Maybe let me make it as 6 7, then I should get an answer 1, that yes, this array is sorted. So now you can see this code is working perfectly fine, and this is exactly how we have discussed the code should be implemented. Okay, so some people may find another way to implement it. Let me also go through that way. So some people may find this array plus 1 and n minus 1 confusing, then maybe is sorted, and you may like to pass an index. Okay, let me tell you one more way. So in this way, you are not changing the value of n. So what we are going to do, we are going to pass the address in the form of an index. Okay, let's say we are checking whether array of I is less than array of I plus 1, and we can say, okay, let us check the remaining sub array that starts from I plus 1 is sorted or not. Okay, and when I reaches this value, okay, we are going to make sub problem. So when I is equal to n minus 1, that means we have an array which contains exactly one element. So let me write the same code in a different manner. So I can check if I equals n minus 1, that means we are at the last index, we can return true. Otherwise we can check if array of I is less than array of I plus 1 and the remaining array is sorted. So is sorted, maybe is sorted 2. This is the second way. Then we pass in the array. Instead of changing the array address, what we can do, we can move the index pointer one step forward, that is I plus 1, and instead of reducing the size of n, we can say the array is from I plus 1 till n minus 1, so we keep it as n, and we can check, we can say return true, otherwise we can say return false. So this could be another way of writing okay, what is not declared, sorry, this should be ARR, this should be ARR. So maybe I can call this method is sorted 2, and here I need to pass in a value of I. Initially it is going to be 0, and if I run this code now, I get yes, it is sorted. But suppose if I put it 16 here and I run this method, now you can say it is going to return 0. So both the methods are almost same. The only thing is in the first method we are not explicitly passing the address, we are changing the base address of the array. In every call we are making a copy of the address and we are updating it. Okay, but in the second address, instead of changing the base address of the array, we have kept a variable I, which tells us in the current function call we are going to start our array from an index I, and we are going to do the work till n minus 1. Okay, so that's all for the two approaches, and I hope the codes are very simple and they should be clear to you now. That's all for this lecture. Thank you. Hi everyone, in this lecture I'm going to talk about a very simple problem, but it's very important to take up this problem for strengthening your concept of recursion. Okay, so we will understand the concept of going towards the base case and coming back from the base case through this example. So you can also try this problem on your own before we dive into the code. So the question is very simple. We just need to simulate the same functionality as of a for loop using this particular problem. So we have to print all the numbers 1 to n recursively in decreasing order and in increasing order. So we need to write two methods. One, let's say if n is, let's say 5, the first method should print 1 2 3 4 5. Okay, the second method, that is for the increasing one. And the second method, if n is 5, it should print the output like 5 4 3 2 1. That is the decreasing one. Okay, now let's see how we can actually do it. So let's say we have a method decreasing which prints the numbers in the decreasing order. Okay, so what we discussed was we will take one step and the rest of the steps will be taken by the recursion. So what I can do in this decreasing method, I can say, okay, I know the value of n, I will first print the value of n. Okay, and then I will call the method decreasing of n minus 1. That will automatically print all the numbers from n minus 1 till 1. Okay, and in the base case we can have a case that, okay, if we are reducing and if we reach a point when the number is 0, we can return. Okay, so let us see what is going to happen if, let's say, n is 5. This is for the recursive case, and for the base case I can check if n is 0, we can return, we don't do anything. Okay, or you could have also have another case like if n is 1, print 1 and then return. That is also fine. Both either of these cases would work. So I can start from, let's say, n equal to 5. What I will do, I will print n, I will print 5, I will make a call on n equal to 4. I'll print 4, I'll make a call on n equal to 3. I will print 3, I will make a call on n equal to 2. I'll print 2, I will make a call on n equal to 1. I'll print 1, I will make a call on n equal to 0. I will say return, it will say return, it will say return, it will say return, it will say return. So finally, what I got in the output is nothing but 5 4 3 2 1. That's how easy it is going to be. Okay, for the increasing order, what we need to do, we need to do the work in this direction. So I will tell you what changes we would make. So let us first write the function for decreasing. So I can say void decreasing int n. So we have a base case. If n is 0, we will stop, that is return, and otherwise I can say, okay, cout the value of n and followed by a function called to decreasing of n minus 1. That's it. So any statements that are written before the function call, okay, so these are executed when you're going towards the base case. Okay, when you're going towards the base case, so anything that is coming before the function call will be executed when you're going towards the base case. Now let me also run this code and show it to you. / increasing decreasing, and I think we should take input the value of n, and then we should call this function. Let's say n is 5, I get the output as 5 4 3 2 1. Now I also want to make a similar function for increasing part. The good thing is there would be only one line of change, that is you will change the order in which this statement is executed. So if I put this statement here, and just to make it more clear, I am going to rename the function as increasing, and you will see this is going to work perfectly fine, and we will see why it is going to work. Okay, so let us try to think what this function is going to do. So let me call decreasing and maybe then endl, and let me call as increasing function as well. So if I say, okay, 5, so I get the numbers in the decreasing order, I get the numbers in the increasing order as well. Let us try to see what this function is saying. So it is saying if you want to print the numbers in the increasing order from 1 to n, you will first print all the numbers in the increasing order from 1 to n minus 1. Okay, and then you will print the number n. So this is the work that is done by recursion, and this is the work that is done by you. In the previous code, what you said, you will first print the number n, and then you will print the numbers from n minus 1 till 1 in the decreasing order. Okay, now you might be surprised how this single swapping of one line of code actually changed the order in which the output is coming. So effectively what is happening is both the functions will have a same call stack. So first of all you have main, then you call the function with, let's say, n equal to 5. Okay, so decreasing function first prints the value, so it prints 5, it makes a call on n equal to 4, then it prints 4, it makes a call on n equal to 3, then it makes a call to n equal to 2, then it makes a call to n equal to 1. and then it makes a call to n equal to 0. So the same calls are being made by the increasing function as well. Okay, so if you pass in n, it makes a call to 5, then it makes a call to 4, then it makes a call to 3, to 1. Okay, but the change is it is printing the statement after the call has been executed. Okay, so after we have returned from the base case, it is going to print 1. After we have returned from 1, it is going to print 2, then it is going to print 3, then it is going to print 4, then it is going to print 5, and that's it. Okay, so this output is generated by the increasing function, and this output 5 4 3 2 1, it is generated by the decreasing function. So here anything that is written before the function call is executed while going towards the base case, that is from the top to the bottom. Okay, so I'm calling bottom as the base case. Okay, and when you're coming from the bottom towards the main thing, that is top. Okay, so this is top is n and base case is 0. So top is n, base case is 0. So when you're coming from a smaller problem towards the bigger problem, then that code is written after the function call. Okay, so that is something you should always remember, and it is going to help you a lot while solving recursion problems. So when you need sub problem solutions to be solved first and then combined, then you would be doing this work after your function call. Okay, so I hope these two concepts are now clear, and that's all for this lecture. Hi everyone. In this lecture, we are going to talk about a very simple problem, that is finding the power of a number. Okay, so let me just tell you what the problem statement is. We are given a number a, and we are also given a number n, and we want to compute a raised to the power n. For example, let's say a is 2 and n is 10, then 2 raised to the power 10 is equal to 1024. So let's see how we can write this. Okay, so a raised to the power n can be written as, if we talk about the recursive breakdown, it can be written as a multiplied by a raised to the power n minus 1. So this can become our sub problem, and once we know the answer for the sub problem, we multiply it with a and get a raised to the power n. So that is one way of breaking down this problem. So first let's see this way, and in the next video I will teach you an optimized way of doing the same. Okay, so let's quickly code this up, and we will also verify how this power function is going to work and how much time and space it is going to take. So let's think about the base case. So what is the smallest possible value of n? So it could be 0. If n is 0, then a raised to the power 0 is going to be 1. We can simply return 1. Otherwise I can return a multiplied by power of a raised to the power n minus 1. That's it, and we are done. So we will take input a and n, and we will compute a raised to the power n. So yes, we are going to do it. Let's build the code, and let me show it to you. So maybe 3 and 5. So 3 raised to the power 5 is 243, and maybe 2 and 10, it is 1024. Working perfectly fine. So let's have a quick look how this is working. So basically, let's say you're doing 3 raised to the power 5. So you have main. From main you make a call as to this power function. A is 3. So a is always 3. So you say it is 3 raised to the power 5. So it says, let me break it into 3 into 3 raised to the power 4. So it says, okay, here n is 5. Here we will compute 3 raised to the power 4. It will make a call on 3 raised to the power 3. Here it will make a call on 3 raised to the power 2. Here it will make a call on 3 raised to the power 1. And from here it will make a call on 3 raised to the power 0. So when this is 0, it is going to return 3 raised to the power 0, that is 1. So 1 multiplied by 3 is 3. So 3 comes here. 3 into 3, it is 9. So it becomes 3 into 9, 27. And 27 into 3 is 81. And 81 into 3 is 243. That's it. This is how we get this particular answer. So talking about how much time it will take, it has performed n number of steps. It is order of n. How much space it is going to take, it is also order of n. Okay, So I hope this is now clear to you. And in the next lecture, I will teach you an optimized way in which you can reduce the time and the space complexity of this program. See you in the next lecture. Hi everyone, in this lecture we will see how we can reduce the space and time complexity of this program that we have just done. Now the question is, we cannot reduce the space and time without changing the recurrence. Okay, so we need to think, is there any other way to write the power function? Can we break down this function a of n maybe in terms of some other term? Instead of saying n minus 1, can we reduce it in terms of f of a comma n by 2? Okay, so the answer is yes, it is doable. How? Let me just tell it to you. So I can write something raised to the power n as something raised to the power n by 2 square of this term when n is even, and if n is odd, then I will multiply this result with another a. Okay, when n is odd. Okay, so you can easily see, if it is like 2 raised to the power 7, then you can say it is nothing but 2 into 2 raised to the power 7 by 2, that is 3, and square of this term. So effectively what we are doing, we are reducing a problem of size n to a problem of size n by 2. From here we are doing it to n by 4, n by 8, and eventually ending up at 1 or 0. Okay, so effectively if we talk about the number of steps that would be needed, that would be log of n. Okay, so instead of doing n steps, we can actually do this problem in log of n steps. So effectively we are going to use this as our recurrence to solve this problem, and let's see how this is going to work. So maybe I can say int fast power, I get a, I get n. Base case will remain same. If n is 0, I'm going to return 1. Then I'm going to check if n is odd. So if n and 1, that means it's odd number. We are checking the last set bit. Then I can compute the answer for the sub problem. I can say, okay, sub problem is nothing but fast power of a comma n by 2, and I'm also going to square this up. So sub problem square. So that is going to be sub problem into sub problem. Now we already know the squared answer. If n is odd, we are going to multiply the squared answer with a, that is a multiplied by sub problem square, and if n is even, we are simply going to return the sub problem square. That's it. That is our final answer, and we are done. So if I now run this code, cout fast power a comma n and l, and we are going to run this one. So dot slash power, if I give 2 and 10, I get the same answer. If I give 3 and 6, I get the same answer. Okay, so both of them are returning the same answer, but the thing is, here we are taking a less number of steps. For example, I'm computing 2 raised to the power 10. Okay, then it gets broken as 2 into 2 raised to the power 5 and square of this term. So we are only computing this term. So here it gets broken as 2 into 2 raised to the power square and square of this term. Okay, so this is written as 2 into 2 raised to the power sorry, not 2, 2 raised to the power 1 and square of this term, and this is written as 2 into 2 raised to the power 0 and square of this term. Okay, this answer is now what? This answer is 2. This answer is 2 square, that is 4. This is 4 is added here, that is 4 square is 16 into 2, that is 32. And if you put 32 square, something like this, so that would be, I think, 32 into 32, that is so this is 2 square 4, sorry, this should be 16. Okay, so this should be 16, and 16 square is 256, into 2 is 512. So we are actually doing 512 into 2, that is 1024. So I hope you're getting this one. We are doing it right, and this is actually perfectly fine. But the idea is, it is going to take log of n steps, both in terms of space and in terms of time. Okay, so that is an optimization, and I hope you really understood this problem. That's it. See you in the next lecture. So you have learned the basics of recursion. Now we would be looking at some quick thinking problems, and we would see how you can create recurrences for some of these problems. Okay, so the idea is, how do you break down a problem and you find out the recurrence? Okay, so let's go through this question. Given a 4 cross n board. Okay, so you're given a 4 cross n board and there are tiles of size 4 cross 1. You need to find the number of ways to fill the given board using 4 cross 1 tiles. Okay, so basically there is a tile of 4 cross 1, or it could be like this also, 1 cross 4. So a tile can be placed horizontally as 1 cross 4, or it can be placed vertically as 4 cross 1 tile as well. So let's see how we can solve this problem. So we are given board like this. So it is 4 units long and n units wide. What you can do, you can put a tile inside this board either vertically like this, or you can place tiles horizontally like this. So to fill up this vertical space, you would need 4 tiles in this case, or maybe again you can put vertically or horizontally. So you need to find out in how many ways are there to fill this board. Okay, so what we have learned in recursion is, we will try to break down this problem into smaller sub problems. So what I can say, okay, let's say we have a board. Okay, and what can be possibilities of filling this board? Let's say this is the board of size n, and let us suppose we put the first tile in the vertical orientation. Okay, we fixed this tile. So what we are left with? We are left with a sub problem. So what is the sub problem? This is the sub problem of size what would be the number of ways to fill the remaining board. Okay, so this sub problem is of size n minus 1, because we have already put one tile in this orientation. Okay, so, or what could be the another option? Another option could be, we first put the tile in the horizontal layout. So if you put a tile like this, then you cannot place tiles vertically on the top of it. You have only one options to place tiles on the top of it, and that is, you have to place all these 4 tiles horizontally. So we have placed 4 tiles, t1, t2, t3, t4, but this is only one combination. Okay, this is one combination, and we also need to find out in how many ways we can fill out the remaining board. Now we know this tile length is 4 units, this is also 4 units, and this is what? This is n minus 4 units. So can I say, if f of n is the number of ways to fill this entire board, then f of n would be equal to sum of these two options. There are only two options to start with. Either you place the tile vertically or you place it horizontally. So the number of ways to fill this board would be f of n minus 1, and the number of ways to fill this board would be f of n minus 4. So can I say f of n is nothing but sum of these two options, that is equal to f of n minus 1 plus f of n minus 4. That makes sense. Okay, so that is the recurrence that you can easily code up to find out in how many ways board can be filled. Okay, now you got the recurrence. You need to think of the base case. Okay, you need to think of the base case. So can you say, if n is 0, there would be only one way. Okay, or if n is 1, then also there would be only one way. What about n equal to 2? So n equal to 2 is also one way, because if you have a board of size 2, you can only place 2 tiles. If you have n equal to 3, then also you have only one way. If you have n equal to 4, okay, so n equal to 3 is also one way. But if you have n equal to 4, then you have two ways. Either place all of them as vertically, or you place them as horizontally, like on the top of each other. So it would be a 4 cross 4 board. So in this case, I can say that for n that is less than equal to 3, the answer is 1. So base case would be, if n is less than equal to 3, I will return 1. Okay. Otherwise, I will return answer as f of n minus 1 plus f of n minus 4. So this is your base case and this is your recursive case. So you can also verify from the recursive case that if board length is 4, then your answer is f of n minus 1, that is f of 3, that is 1, plus f of n minus 4, that is 0. So that is also 1. Okay. So that means for n equal to 4, using this recurrence, you get the answer as 2, which is also true because we have seen these diagrams. Okay. So I hope you have understood this problem and you can easily solve it using recursion. And later on, once you learn dynamic programming, you will find that this problem also has overlapping sub problems. Why? So let me tell you what happens if you compute for n equal to, let's say, 6. So you make a call on n minus 1 and n minus 4. You're making two calls. You make a call on 5 and you're making a call on 2. From 5 you're making a call on 4 and you're making a call on 1. From 2 you're making a call on 1, and 2 is actually a base case. Okay, so it is less than 3, you're not making a call. So from 4 you would be making a call to 3, and from 4 you're also going to make a call to 0. So let's take a bigger example. Let's say n is 7. So 7 minus 1 6, and 7 minus 4, that is 3. So what you can observe is there would be some states which you are computing again and again. Okay, that is the concept of overlapping sub problems that we would do in dynamic programming. And in that case you can add some optimization to just make it work in linear time. Okay, so that we are not concerned right now. The only thing was you should know how to drive the recurrence and how to solve this problem. I hope that is clear. Hi everyone, so welcome to the yet another video on a recursion problem. So this time we are discussing the problem binary strings. The question is we need to count the number of binary strings, basically all the strings which are formed using 0 and 1 and with no consecutive ones that can be formed using a string of length n. Okay, for example, let's say if I give you n as 2, how many binary strings you can form? You can form, let's say 0 0, 0 1 and 1 0 and 1 1. So this is a binary string that is not a valid in this case, so we'll cross it. For n equal to 2 we have 3 binary strings. Okay, and what about n equal to 3? So total we know we can form 8 strings. Let's say we have 0 0 0, it is valid. We have 0 0 1 valid, 0 1 0 again valid, 0 1 1 not valid. Okay, or that's what we are going to have. Or maybe we can have 1 0 1, this is also valid. Okay, so invalid strings would be 1 1 1, 0 1 1, 1 1 0 and 1 0 0, it is also valid. Okay, we have 1 2 3 4 5 6 7 8. So out of 8 we don't have this one. This is invalid, this is invalid, this is invalid. We have 1 2 3 4 5. We have 5 strings which are valid. Okay, so a brute force way would be you generate all possible strings and then eliminate those which are not valid. But let's think if we can come up with a better algorithm to solve this. So now let us try to break down this problem recursively. So what I want to generate string of length n. Okay, I want to generate a string of length n. So what I can do is I can say, okay, I can put the first bit, the first letter as either 1, or I can put that as 0. So I can say, okay, I will put the first thing as 1 and I will count. Let me just put this thing like this, and let me say I will put the first thing as 0. The first number is 0. So what is going to happen in this case? We are left with remaining n minus 1 positions. We are left with remaining n minus 1 positions. Here also we are left with remaining n minus 1 positions. What I can do, I have two options at the first index and we are trying to form the sub problem. So if you put the first number as 0, then you clearly know that the remaining sub problem can be solved if I say the total number of ways to form number of binary strings without consecutive ones for this problem of size n, if this answer is f of n, I can say this answer would be nothing but f of n minus 1. Okay, because you can put 0 here, 1 here, it doesn't matter. You can put anything, that will not matter. But this sub problem will make sure that there are no consecutive ones in this array of size n minus 1. Okay, but here there is a problem. If you put a 1 here, okay, there would be a consecutive one, and that would lead to an invalid case. So what you need to do, you need to say that this position would always be 0. If you have a 1 at the first index, then the next index must be 0. Then what you can do, now this is a very similar problem. Now you have a fixed 0 here, you have a fixed 0 here. Okay, and what you can say, we can solve this problem which is of the size n minus 2 in f of n minus 2 ways. Okay, so now it doesn't matter whether we put a 0 here or a 1 here, but this recursive property will make sure that we don't have consecutive ones in this array of n minus 2. So we have no consecutive ones here. So what we can say, f of n is nothing but sum of these two cases, f of n minus 2 plus f of n minus 1. So you can say f of n minus 1 plus f of n minus 2. So what would be the smallest case? If n is 0, we can say 1. The null array is one way. If n is 1, there are how many ways? There are two ways. Okay, either we put it as 0 or we put it as 1. If n is 2, we saw that there are three ways. So if you use the recurrence, that f of 2 is nothing but f of n minus 1, that is f of 0 plus f of 1. Okay, so this is coming to be how much? 1 plus 2, that is 3. That's great. What about n equal to 3? So for n equal to 3, we know we are making a call on 2 and 1. So 3 plus 2 is 5. And we just saw in the example that for n equal to 3, we have 5 ways. And for n equal to 4, it would be 5 plus 3, 8 ways, and so on. So this is how you can easily solve this problem. You can use recursion, and if you know about little bit about dynamic programming, you can use top-down or bottom-up DP to improve the complexity of the recursive solution. Okay, so what would be the complexity of the recursive solution? So you are making two calls at every node, n minus 1, n minus 2, n minus 3, n minus 4, and this is going to take order of how much? 2 raised to the power n time, because it is very same as Fibonacci, order of 2 raised to the power n time. But using memoization, this can be reduced to linear complexity as well, and using matrix exponentiation, which you have already learned. Okay, you have already learned, or maybe if you have not learned. Okay, so depending upon if you know a technique to solve linear occurrences, you can also reduce it down to order of k cube log n. So k is the number of terms on which this n is depending. Okay, and this is 2 in this case, so order of 8 into log of n. This can be solved in logarithmic time as well. Okay, if you use this technique, matrix exponentiation, for linear occurrences. If you're learning the basics of data structures, you're not supposed to know this, but if you're doing competitive programming, you are supposed to know this technique. And this is the basic recursion complexity. If you use DP, it can be done in order of n, and using matrix exponentiation, it can be done in order of k cube log of n time. So I hope that is clear to you, and that's all for this video. Hi everyone, so we are discussing another problem. It's a popular problem on recursion, you can say. It's known as friends pairing problem. So given n friends who want to go to a party, and each of them can remain single or can be paired up with some other friends. Let's say there is a party happening in Goa. Okay, maybe you want to go to this party, and what people can do, people can either go solo or they can pair up with someone. Okay, they can go as a couple as well. So either you can go single or you can go as a couple. So each friend can be paired only once. Okay, you cannot make pairs with multiple people, find out the total number of ways in which friends can remain single or can be paired up. So let us take an example of let's say we have 3 friends. Okay, so what we can do is A, B and C. Now all of them can go as single, so there is one way. A goes alone, B goes alone, C goes alone. Or maybe A and B decide to pair up and C goes alone. Or maybe A and C decide to pair up and B goes alone. Okay, or maybe A and B and C decide to pair up and A goes alone. That is also possible. Okay, if you had 4 friends, like for n equal to 3, the answer is 4. If you had 4 friends, then there would have been even more combinations. Even all of them can go solo, or in the best case all of them can get paired up. Maybe A and B pair up, C and D pair up, A and C pair up, B and D pair up. Okay, or maybe A goes alone, B goes alone, C and D pair up. So there are so many ways. So you need to find out in how many ways you can pair up these people, or or they can also go as single. Some of them can go as single, some of them also can pair up. So that is the question. Now let us discuss a possible approach to solve this kind of a problem. So again, idea is we try to break it down. So we have n people who are standing in a row, let's say, and there is this guy, let's say A, and now we will only talk about what are the options for A. Okay, let's say it has B, C, D up to whatever. Let's say we have up to n people. Now if A goes alone, there is one option. If A goes alone, then what is going to happen? The remaining people, okay, so A can go alone in only one way. There is only one way for A to go. That okay, A will say okay, I'm going to the party, rest of you manage by yourself. If there are f of n ways for all of these people to go to the party, for n minus 1 people, there is how many ways? F of n minus 1 ways. A is also going and these people are also going. So A and these people are going. So A is going alone, so there is only one way in which he can go alone. So it would be 1 multiplied by f of n minus 1. Because there is an and. A is going and n minus 1 people are also going. Or what we can have, A says no, I want to go with my girlfriend. Okay, so A wants to pair up. So A wants to make a pair with someone. Okay, so that could be anyone. Maybe that could be this girl, or maybe that could be this guy. A might pair up with this one or this one. So A has how many options to make a pair? So obviously we have n minus 1 people. So A has n minus 1 choices to pair up with someone. So A says okay, I will pair up with someone in n minus 1 ways. So how many people are left in the remaining array? So you are left with n minus 2 people. So A can go with someone in n minus 1 C1 ways. Okay, that is nothing but n minus 1 into, and the remaining people are also going. So they can go in how many ways? That is f of n minus 2. Okay, so your final answer would be sum of these two. So or means plus. So 1 into f of n minus 1 plus n minus 1 into f of n minus 2. So we can write f of n as, f of n would be nothing but sum of f of n minus 1 if A goes alone plus n minus 1 into f of n minus 2. That is the recurrence. Okay, that is the recurrence that we have created. Now what about the base case? If there are 0 people in the hall, one way. If there is 1 person, there would be one way. If there are 2 people, then either they go alone, let's say A and B, or they go as a couple. There are 2 ways. So we'll try to derive this using this recurrence. So we can say f of n equal to 2 should be 2. We can also verify n minus 1 is what? 1 plus 2 minus 1 is 1 into f of 2 minus 2, that is 0. So that is also 1. So it is nothing but 2. So f of 2 is 2. What about n equal to 3? So n equal to 3, we will say f of 3 minus 1, that is f of 2, that is nothing but 2, plus n minus 1, that is what? 3 minus 1, 2, into f of n minus 2, 3 minus 2, that is f of 1. F of 1 is how much? 1. 2 plus 2 is 4. We just saw that for n equal to 3, the answer is coming 4, and that is also true because we discussed ABC can go alone, AB can go together, C can go alone, BC can go together, A can go alone, or AC can go together, B can go alone. So these are the four ways. So that means the recurrence that we have derived is correct, and it will work for all values of n. Okay. So again, the time complexity is going to be exponential, but it can be reduced to linear very easily using memoization if you know little bit about dynamic programming. All right. So that's all for this video. Thank you.
Hello everyone, welcome to one of the greatest problem of recursion, and today we'll be solving the Tower of Hanoi problem. If you do not know about it, then it's a very simple and easy problem. I first met this problem in a movie called it was Rise of the Planet of Apes. So what is the point of this problem? This problem is simple that in you have three rods, right? So initially you can see we have three rods A, B, C, and you have n disk, right? And you can see these are the four disks initially, 1 2 3 4, right? What you have to do is you have to place these n disk. You have to pick these n disk and place these disks from rod A to rod C, and you can use rod B. So what's the catch here? The catch here is some of you might be wondering, like, just pick it up and place it. No. So the catch is you can just pick up one disk at a time, and the second thing is you can only place a small disk on the top of the bigger disk, right? That means you cannot place a small disk on B and then a bigger disk on B and then a more bigger disk on B. This is not possible. So a small disk can only be on the top of another bigger disk, right? We have three rods, we have n disk. In our case, n is 4, and what we have to do is we have to place all the disks from A to rod C by using rod B, right? What do I mean by using rod B? Means I can use rod B in any way, but in the end, my problem will be solved when the situation of these rods are like this. All these rods are on C, right? And of course, there won't be any rods. Cool. So this is the final situation, the final condition of my problem. So okay, so let's play this game for some very small number of rods initially. Let me copy this. Hmm. Yep. So let's say right now I just want to make the problem very clear. Let's say I have only um two disks. Cool. So what's the best way to move both these two disks to C? Uh, if I place the okay, let me give them numbers. So we'll always number them according to their size. So one will be the disk with the smallest size. Second will be the bigger disk, right? So in the first step, what I can do is I can pick up the smallest disk from A and move it to C, right? So what is A to C? A to C means only one thing, that the disk which is on the top of A is picked and moved to C, right? So we don't have to mention one or two over here because there will be exactly one disk on top of any of the rods, right? So if I move it from A to C, then the second step can be I can then move from A to B. That means after performing A to C, what happened? This thing happens, right? Now after performing A to B, what happens? I'm picking up this disk and I'm moving it to B, right? So let me pick it up and move it to B. So this is a bigger disk. Cool. And now let's say I'm moving a disk from C to B, right? Because see guys, now I cannot move a disk from B to C. Is it? Yeah. So I cannot move a disk from B to C because the disk at B is greater than a disk at C. So if I move a disk from B to C, this will happen. But this is exactly what we don't want, right? A smaller disk cannot be down of a bigger disk. Cool. So always the disk should be in ascending order, right? And yeah, now as we can see, we are kind of stuck over here, right? Or what we can do is we can do this also, that instead of B to C, let's say C to A. So this small disk reaches A, and finally B to C, So B starts from here, reaches here, and then the last one can be A to C. So A reaches over here, right? So A to C, then A to B, then C to A, then B to C, and then A to C, right? So in this way, we are placing these two disks from A to C, right? But some of you might be wondering that of course this is a possible way, but is this the shortest way? No, right? So I always want the shortest way to pick the disk from A and keep the disk to C, right? So this is of course not the shortest way. So let's see what is the shortest way. You can of course pause the video and think about it yourself. I'm taking an example of two disks because it's easy to understand. You can try this for three disks as well. Three is a very nice example. Yeah. So let's find the shortest way, right? So in the shortest way, what we can do is, instead of making A to C move, let's make A to B move first, right? So A to B, what happens? This shorter disk reaches B. Now let's move A to C. So the bigger disk is here now, and now let's move B to C. So B to C. So the shorter disk is on the top of C. So this is exactly what we want, right? We want to use B. We want to start placing the disk from A to C, right? So yeah, I hope there is no doubt here. Of course, you feel free to try this for three disks, right? So here you can see the shortest path was for three length, right? So in just three steps, I was able to move two disks from A to C using B. Now, you all can try what will be the best way to move these disks from A to C using B. And now the number of disks is three, right? So I'm just leaving this to you. Maybe pause the video and try to do it yourself. You will understand the problem. And just keep one thing in mind. Uh, just a bigger disk, if there's a bigger disk in any rod, it will be the down, right? That means there should be no bigger disk on top of any of the smaller disks. Cool. Yeah, so we just need to keep that condition in our mind, right? Now let's see how can we use recursion to solve it, right? What does recursion always do? We always know that recursion is nothing but dividing a problem into sub problems, right? And asking that, okay, to solve this problem, why don't you solve the part of it? We will make a move and then do solve another part of it, right? Basically, uh what we'll do is we'll divide these n disk into parts, and we'll say, why don't you just solve this part, because that will be a same sub problem, right? That is moving disk from a particular rod to another particular rod. And we will say that, okay, you solve this sub problem, and then you solve the another sub problem, you solve the another sub problem, and then finally a problem would be solved, right? So let's see how can we divide this tower of Hanoi into some sub problems. Cool. So I'm taking this example of I would prefer four rods or three rods. Let's take any. Okay, let's say I have this example of three rods. Cool. So let's try to understand what we'll do by using recursion. So we have three rod. Right now my n is equals to 3, and now you know what does A to C, B to C means. N is equals to 3. Right? So initially what we will say is, let's say we have a function that will solve this, and let's call it Tower of Hanoi. Tower of Hanoi, right? So in short, what I'll call it F. Cool. So what will F of initially the disk are n, it is 3 in a case, we'll see that. So Tower of Hanoi, which is F and A comma B comma C, what will it do? What does this represent? It will represent that place n disk from A to C using B. So here is just another concept, which is which it's not a new concept. It's just we'll just name them, right? So here you can see it is A B C. So instead of A B C, let me write it in a generic way, right? That F of n comma from rod. That means from where we are picking these n rods, means from where we want these n rods to be picked, and the third variable will be the aux rod. What is aux rod? It is auxiliary rod, which is the helper rod, right? So we can call it helper rod as well. Let me call it helper rod, right? So it's the same case, right? We are using we have to pick up the disk from A. We'll take the help of B and we'll move them to C. And the third one is to rod, like where all these end disks should reach in the end. This is my state of recursion, right? So this is what I want recursion to solve, right? So what should be my initial call of the recursion? I'll just simply ask the recursion that go take 3 in this case. Let me write it here. So this is my initial call, which is n 3 comma a comma b comma c, right? So place the 3 disk from a to c by using b. But how will you do it? That's the most important part, right? So now just let's just think about it. Let me, yeah. So let's just think about it. We want 3 disks from A to be moving to C by using B, right? So so now tell me what will be the final case? Like what should be the end step of this movement? Let's say we have finally moved, right? The end step, that means let's think far ahead, and we'll think what is the end step, right? So in the end, guys, what would be happening? Let me, yeah. Actually, what we are doing is we'll just trace it from back, right? So this is the end condition that we want. For this end condition to fulfill, what is the last step that would have been performed here? So can I say that the last step is placing yeah, let me quickly. Can we say can we say if we get this as a state, that means two that means two yeah, that means first two disk on B and the last disk on C. Then we can simply solve it by placing this one over here, two over here, and then one back over here, right? So basically, if we are able to figure out this state, then we can figure out the final state, right? Or in short, what I can say is this is also possible, right? That I ask recursion to place the two disk on B, right? Instead of all the three disks to C, I'm just asking it to place the top two disk on B. Just place it, right? Basically, this call, which is f of 2 comma um why 2? Because I want it to place only two disk to B, right? So take these two disks from A. Initially, these two were on A, right? Place it to B, right? By using C. Got it? So basically, what's happening? I have three disks. I want to place the top two disk to B by using C, right? That's what I'm asking recursion to do. That's what this function f will do, right? It will just take the two disk, place it on B using C. You don't have to worry about how it is doing it, right? We'll trace it back. But I'm just thinking of it in a sub problem way, right? So, uh, yeah, I'm just making some space. Let me erase things, right? So, okay. Okay. So yeah. So let me just write it over here. Yeah. So if I'm able to place these two disks on B by using C from A, then what I'll simply do is I'll make a move. What is the move that I'm making? I'm saying now make this move, which is A to C, right? And now what's the situation here? The situation is simple, that this is the situation after these two steps are performed, 1 and 2. And what will be the third step now? The third step is nothing but, as you can see, again it is a sub problem, right? Now I want to place these two disks to C from B using A, correct? So what will be my function call over here? Place the two disk from B to C using A. I hope this is clear. So let me quickly iterate all these three steps again, and yeah. Yep. So this is what we started with. So so instead of 2, let me write n minus 1. right? Because it will work for all n. So yeah, so now let's say we have 4 of these. Cool. So n is equals to 4. Now what I want is, initially I want, yeah, cool. So initially what I want is, I want f of n comma a comma b comma c is from take all these 4, put it to c by using b, right? How he will do it, we don't have to worry about, right? So, and how we want it to do it is this. Step 1, what to do in step 1, take these 3, right, place it from a to b from by using c, right? So somehow, isn't this a sub problem, guys? Isn't it saying that let's say if I don't have the fourth disk, isn't it this a problem that instead of now moving these 3 disks to c, I want these 3 disks to move to b, right? It's just that our helpers changed. So if I would have wanted it to shift to c, I want b to be helping it, but now I want c to be helping it, because now I want these 3 disks to move to b, right? So basically, initially what's happening, I'm calling this, which is from take the 3 disk from a, move it to b by using c, right? So after this function call is over, that means I have already moved this disk to b, right? That means I'm calling the recursion, I'm saying solve this sub problem first. So the recursion calls another function, and of course that will only work according to the recursion that we have written, right? So basically, this is the first step that's happening, right? So after the function, yeah, now we'll just assume that this is the current state when I reach at step 2. This is the current state of my solution, right? So when I reach at step 2, this is the current state of my solution. Now what is the step that I'm doing? I'm just moving a to c. That means I'm taking the bigger one, moving it to c. That's what a to c means. And now what is the third step that I'm doing is, I'm saying that okay, now again, uh we had n minus 1, we had this n minus 1 disk on b, right? So from b, move those n minus 1 disk to c by using it. Isn't this a sub problem, right? So this is a sub problem, right? So we somehow move these n minus 1 disk to c by using a, and when all of these will be moved, then what will happen, we'll get a final answer, right? Some of you might be wondering, because of course it's a live it's not a live lecture, it's an online recorded video. So you might be also wondering that how will these 3 move to this particular c, right? So let me give you a quick example, right? So this is what recursion is about, and believe me or not, this is one of the most uh, famous and most tricky and most challenging problem that I've seen in recursion, right? And it yeah, so yeah, some of you might be wondering that okay, let's talk about the first step only, let's not talk about the second step, right? uh and what I'll do is, I'll just trace the function calls. Cool. So this is, and right now I'm just taking 3 disks. Cool. So what will happen, yeah, so initially what will happen, I'll just call f3 a b c, move these 3 disks from a to c by using b. So what will this function give me, it will say fn minus 1 acb, right? Which is f2, now the from rod is a still, and move these disks to b by using, sorry, move this disk to b by using c, right? So just don't forget this, and to help, and from help to, right? So this is what we are generally doing. Now this 3abc will call 2acb. That means somehow place these top 2 disks from a to c by from a to b by using c, right? So don't get confused. Cool. Now let's say this function has been called, right? So what was the second step? And there was also a third step for this. Let's just wait. Firstly, this function will be called because we are calling the recursion to solve it. Now, what will this 2ACB do, guys? What will this 2ACB do, right? So 2ACB will again call that f of, because you know it is recursion, right? So n is calling n minus 1, right? Similarly, this 2ACB, now this is a new state. Now this state will call 1, right? So what was this? From A, uh, move those two disks to B by using C, right? So now what will be the new state here? Move one disk from A uh, to C by using B, right? So let me quickly write it here as well. Yeah. So N to uh, help, and it is very tricky. Yeah. From help to, this calls n minus 1 from help to, so this calls from to help. So the new helper is the one at which we are going to, right? So which is this 1 a b c, right? So what will this call? It will call f of 0 from A to C by using B, but we can't place 0 disk, right? So it will come back. Now what will happen? Now this second step will be performed for this state, which is f, yeah, which is nothing but move one disk from here you can see A to C, but here I've written A to C, right? But it is what it is, from helper and to, right? So don't get confused by ABC and from helper to, right? Because they are kind of uh same things for a same state, but ABCs will change. Sometimes A will become from, sometimes A will become helper, and sometimes A will become to rod, right? So don't get confused in this. Cool. So yeah, now what will happen? From 1 A using B, put it on C. So what it will do is it will just imagine 1 has been put on C, right? And now it will do is it will just move A to B, right? So the second rod will come here. That means the first rod is over here. I hope you are getting the whole portion of it. Or what we can do is we can also, it is being very tough for me to make you realize the whole recursion right now over here. But what I can do is I can code it, and then in the code only we can trace it, right? That what are the functions that are being called and what is the movement that is being made, right? And that will be very helpful for me. Cool. So this was the first step, right? NABC. But if I want to generalize it, how can I generalize it? I will simply say FN from helper to, we want to move this. So what do? You firstly move n minus 1 from here only, using where I wanted to go to the helper position, to the helper rod, right? So if this happens, then in the second step you perform this, which is from to, right? That means the because we have moved n minus 1 disk, that means there's only one disk left on the from rod. I'm moving this one disk from rod to rod. Now what's the third step? We had this n minus 1, those n minus 1 are kept and waiting on the helper rod, right? So pick them from the helper rod, use the current rod, which is the from rod, and okay, n minus 1, yeah, pick them from the helper rod, use the current rod, which is now empty because we have made this move, which is f to t, and uh yeah, uh, pick them from the helper rod, use the current rod, which is from, and move them to the to rod. This is a normal recursion that we'll code, right? So in the next video we'll just code it and see, we'll just print down some values and see how it's working. Cool. So yeah, thank you. Yep. So let me quickly code it, and yeah. So initially what we'll do is we'll just of course, so there are two things here, right? First is whether you want to print the number of steps or you actually want to print the steps. So let's do both, right? Or what we can do is we can just print these steps, and then we can realize this realize this tower for it, right? So what we'll do is we'll write a function called tower of Hanoi, and let me write tower of Hanoi int n. So so what we have is we have ABC. What are ABCs? Rod, helper rod, to rod, from rod, right? So instead of, okay, so if we want to keep ABC only, then we need to keep them as characters. Otherwise, we could have taken integers, which is 1, 2, 3 odd numbers, right? Let's take characters only. It doesn't matter much. So character from rod, character helper rod, and character to rod, right? So this is my recursive. Let me. So this is my recursive function, right? So initially, what will happen? I'll just take n. Let's take n, and according to this n, initially it is 10. Instead of 10, let's make it 1 initially, right? So we'll start from 1, then we'll see 2, then we'll see 3. So we'll realize how is this recursion working. Actually, I'm going deeper into this because I want you to understand this, because um it will come very handy in dynamic programming later on. So that's why I'm giving much time to this. So initially, let's say I have moving from A, I want B to help, and I want to move all those n to C, right? So initial state is this are on A, right? So what's the first step that I want this to do? What's the sub problem that I want it to solve? I want it to place the n minus 1 disk on pick it from this only, where I want it to be placed. I want it to be placed on the helper, right? So let me place on the helper, and yeah, sorry, I want it to be placed on the helper. So the new 2, that is character 2, will become helper, right? That means place n minus 1 rods from to helper to the helper rod, and by using the 2 rod, right? So basically 2 becomes the helper and helper becomes the 2, right? In our case it was B and C. Initially I was placing n on C by using B, but now I'm saying place n minus 1 on B using C. Cool. Now when I reached here, when I have reached here, what does it mean? It means that I have placed n minus 1 rods on the B by using C, right? So that's what recursion is, right? That means I have already placed, that means we can imagine that all those rods are lined up on B, only one rod is remaining on C, which was the nth rod. And now what I'll do is I'll just move this nth rod to C, right? So let's move this nth rod to C, nth rod to C, or instead of C, let's say 2, right? So what I'll do is I'll just make a move and we'll say C out from rod, make this move to 2 rod, right? So from wherever the nth one was there, I'll just move it to the 2 rod. And now I have made a move, I have placed it over there. Now what we need to do is we know that right now there are n minus 1 rods on the helper rod, right? So we want to pick them from the helper rod and move to the 2 rod, right? By using the current rod, which is the from rod. So what will be my new recursion here? It will be n minus 1 were on the helper rod, so pick them from the helper rod, use the current rod, which is from, and place them on the 2 rod, correct? And let's write some base cases also. So what are these base cases? What's the base case, guys? Nothing. If n is equals to 0, if there is no rod, because you know n is always reducing, if there's no rod, return 0, right? And let's see what we get. If n is 0, return, okay, sorry, not return 0, it's a void function. I'll just return back because I don't want to do anything. So guys, if I have exactly one rod, that means there is only one rod on A, then I can simply pick that rod from A and place it on C, right? Now let's see what happens on 2. On 2, what's happening? Firstly, I'm picking the rod from 2. Okay, let me, yeah. What's happening? A to B. We have already discussed this, I guess, right? So A to B, A to C, and B to C. So as you can see, guys, what's happening? The small rod from A to B, the second rod from A to C, and the small rod again from B to C. So can you realize that uh, this the first call for this, that means pick up one rod from this by using C, place it on B, right? So I'm just placing it directly on B because it is exactly one rod. So isn't that a sub problem? To solve two, first solve one, right? To solve one, first solve zero. So basically for let's talk about three. To solve three rods, solve two rods to B, right? So right now what we are saying is just ignore the third rod. um Place the two rods on the helper node somehow. That's a sub problem, right? So that now solve it for two, place it on the helper rod, and by using the final rod. So pick the last rod, place it there, and then put all those two back, right? So that's what Tower of Hanoi is doing. And yeah, let's try it about three. Of course you can okay, do you want me to print what's going on? Okay, let's print this as well. I know it's a little tough to understand. I'm trying my best here. So yeah, okay, okay. So 3 ABC will call 2 ACB, which will call 1 ABC, right? So that means 3 ABC goes here, calls 2 ACB, which calls 1 ABC, which calls 0 ACB. But we know we don't have to worry about 0, so I'll just print it down that we don't get 0 wale cases. Yeah. So 3 ABC calls 2 ACB, calls 1 ABC. Now when 1 ABC is called, we'll just what does it mean? That just place one rod from A using B to C. So what we have done is we have just placed that one rod from A to C, right? And now what will happen? We'll go back once, because as you can easily see, if there's just one rod to place, right? So now this will be called, which is n minus 1 helper from 2, right? So again that will be so for 1 that will be a 0 thing, right? That's why it's returning from the base case. And now we'll just place A to B now. So I don't know if I can like try harder here, but I hope you have understood. Cool. And just one small thing to keep in mind, it is just dividing into sub problems. And that sub problems are independent of my current problem, right? If I have three disks, I'm solving it for two disks, so that those two disks are actually considering that these three disks are not there, this the third disk is not there. So solve that for two disks somehow by ignoring the third disk. And if that two disk is solved, just please keep the third disk wherever it wants to be, and now again solve for those two disks by ignoring the third disk, right? And yeah, let me comment it. Let me make it for 4. So one thing that you will realize here, that for 3 there were 7 steps that we could have done, right? For 4 we have 15 steps. For 5 we have 16, we have 31 steps. Great. For 6 we have 63 steps. So is there something that you can realize, that the answer is always equals to 2 raised to the power n minus 1, right? So yeah, so for 10 it will be 2 raised to the power 10 1024 minus 1. So you can see that I don't think any human would be able to solve this tower of Hanoi for 10 in I mean they can solve it, but uh, they might not solve it as well. So it's taking 1023 steps, and if you perform all these steps one by one, you will realize that yes, this is the final solution. So that's what recursion is doing, right? So that's how we want to use recursion, right? We don't want to think how he is doing it. We just want him to do it. That okay, do this I will do, and then this you do it again. Nothing else. Cool. So thank you everyone, and see you in the next parts.